Hello. This presentation will introduce the multi-phase version of Darcy's law and the concept of relative permeability to describe through a porous medium the flow of more than one fluid phase. So instead of a porous medium containing just water, for instance, we may have water, oil, and possibly gas also present. So how do we describe that mathematically? So let's go straight to the equation that illustrates it. This is shown here on this slide. So the equation at the top is the single phase Darcy law. Q is the volume of fluid flowing per unit area per unit time. And it is proportional to this term grad P minus rho G. That's the pressure gradient, and then a term due to gravity. It's inversely proportional to the fluid viscosity, and the capital K is the single phase permeability. In multi-phase flow, we have exactly the same equation, but now that symbol P labels the phase, oil, water, or gas. So let's imagine the flow of water, for instance. In single phase flow, we have the top equation. If we now have the flow of water with the same pressure gradient on the water, but there's also oil in the pore space, then the water doesn't occupy so much the rock, and so its flow, one must assume, will be lower. So QP, which is the volume of phase P, water in this case, flowing per unit area, per unit time, will be lower. And it will be lower by a factor, which is this little KRP, right, lowercase k, which is called the relative permeability. So from an engineering perspective, it simply gives us a relationship between flow rate and pressure gradient and how it has decreased, how the flow rate has decreased due to the presence of the other phases in the pore space. So that's the concept of relative permeability. Rather obviously, you can see that it is a function of saturation, the fraction of the pore space that's occupied by each phase. Again, if we consider water again, if there is no water, if the water saturation is 0, the relative permeability of water must be 0. If the water saturation is 1, then it's single phase flow, so the relative permeability by definition is 1. Okay? And it will increase between 0 and 1 as the water saturation increases. The final concept here is we talk about the flow rate as being proportional to the pressure gradient in each phase. But the phases themselves can be at different pressures because there is an interface between them through the Young-Laplace equation. And so there is also a capillary pressure, which is the pressure difference if we're in an oil-water system, traditionally the oil pressure minus the water pressure. That is also going to be a function saturation. So that is relative permeability mathematically, but it is something that simply has to be measured. So how do we measure it? Well, we would take a piece of rock, often about this size, maybe larger, in some cases smaller. We will then encase it in a sleeve, which enables us to apply high pressures and temperatures that are representative of the reservoir that we want to study deep underground. So we're reproducing inside the rock what it is like deep underground. And then what we're going to do is we're going to have to inject two phases. So one method of doing this is called so-called steady state relative permeability. I'm going to inject both oil and water through the core, and oil and water. And I do this for quite some time until one assumes that we just have the same amount going in as out, and within the core, a constant saturation. Through the pumps, we also impose what we call the fractional flow. The water fractional flow is the Darcy flow rate, so it's the volume of water flowing per unit area per unit time, divided by the total velocity, the total Darcy velocity, which is the sum of both oil and water. And what we can do is we can change that in increments. So we can imagine an example where we start off just injecting oil. So there may be some initial water present, but it's only oil that's flowing. And then we, in small increments, increase the amount of water, wait until we reach a steady state, do it again, do it again. Okay. And so that would represent what happens in a water flooding process where water displaces oil. You might say, well, how do I actually get the relative permeability from this? Well, the first thing you need to know is the saturation. You can get the saturation either from imaging, I'm going to show that in a few slides, or from mass balance. You know what comes in and you know what goes out, and you, one assume, has measured what was in there originally. But you also measure the pressure difference. So that delta P in the diagram, that's the pressure difference across the core. So you know the pressure difference, you know the fractional flow. It's actually relatively straightforward then to back out the relative permeability. There is one major approximation you make, which actually makes these experiments very difficult to do, is that you also have to assume that the capillary pressure across the core is constant. And that's not straightforward to impose. But as we're going to show later in some of the results, if you have in situ imaging, if you can actually look at the pore scale configurations of fluids, you can in fact measure the capillary pressure from the curvature, the interfacial curvature that you observe. You can see if it's constant or not, and if it's not, actually, you can correct for it. These are still difficult experiments because you have to impose reservoir conditions of temperature and pressure, and you also have to ensure, obviously, that the oil and water are uniformly distributed throughout the rock. The relative permeability is a function of saturation, and that's normally how it's plotted. But the behavior will also depend on other things, and sometimes people get quite excited about this, but there's nothing mysterious about it. It will depend on displacement path. If water displaces oil, for instance, the oil will be trapped. And that's different from what happens when oil displaces water in a water-wet system, where the water is not trapped or is just retained in the corners of the pore space. So the relative permeability depends on displacement path. It will also depend on flow rate. If I flow much faster, I can sort of push blobs of oil through the pore space. And flow rate is normally encapsulated in what's called the capillary number, written here. The capillary number is a dimensionless ratio of viscous to capillary effects. Mu is the viscosity, normally the viscosity of the phase you're injecting. Qt is the total velocity. Sigma is the interfacial tension between the two. But it will also depend on the wettability, how much each fluid likes the solid surface, and the pore structure itself. Okay, so that the relative permeability is not a unique function of saturation. So now let's show some results here. These are results from imaging. So what have we done here? We've taken a sample of rock, actually a rather smaller sample of rock than this, one that's only 5 millimeters in diameter, so that we can actually image inside the pore space. Okay? And the top row shows a sequence where we start with a rock with a small amount of water initially present. That's true in any oil reservoir, so it's reproducing natural conditions, which is shown in blue. And the red is the oil, which is in the larger pore spaces. And then we just inject oil and we image. Then we have a fractional flow of 0.3, which means 30% of the flow is water, 70% is oil. So now we put some water into the pore space, more water into the pore space, and you can see now that the picture gets more blue. And then we increase the fractional flow until it's 100%, so we're just injecting water. We don't get rid of all the oil because the oil is trapped in the larger pores. So what we tend to find here is the water is in the small pores, the nooks and crannies of the pore space. The oil is in the larger pores. And the sample that we're looking at, like this, is a simple water-wet sandstone. So the grey are the grains, blue is water, oil is shown in red. What's shown lower down is the same experiment, but at a slightly higher flow rate. The flow rate we have at the top, I don't want to go through the details, but that's sort of typical of what you might see in an oil reservoir. The flow rate we're seeing lower down is rather faster, what you might see near a well, or if you were to reduce the interfacial tension, so the balance of viscous to capillary forces changes. You see much the same behavior, of course. You start off with mainly oil, you're ending up with just a small amount of oil trapped in a few of the large pores. But if you look carefully, it's not that evident, but if you look carefully, there's some regions here that are yellow. And you might think, well, what's yellow? The yellow represents regions where, over about an hour to take this image, some of the time the pore space was full with water, sometimes with oil, so there was some sort of fluctuating occupancy. There's still a well-defined relative permeability, but here now, the flow pathways are not fixed. At very low flow rate, what we see is oil is flowing in its path, water is in its path, and it's completely segregated. So they have their own, I might say, sub-pore space through which they flow. We increase the flow rate, we begin to see some sort of intermittent, some regions of the pore space occasionally have a flow of water, sometimes of oil, and of course that will affect the relative permeability. So the relative permeability is a function of saturation, as we can see here, but also of flow. So now let's look at what does a relative permeability look like. Here we have some classic experimental data from the literature, which is shown in red, again on a water-wet sandstone, Berea sandstone by oak. The first curve on the left here is for primary drainage. So what this represents is a piece of rock that initially is full of water, then oil is injected, and we increase now the fractional flow of oil. So what do we see in terms of the relative permeability? To begin with, right, here we have relative permeability against water saturation. We start with a water saturation of 1. The water relative permeability by definition is 1, and there's no oil, so the oil relative permeability is 0. And now what we do is we increase, right, if we're increasing the oil saturation, we're decreasing the water saturation. So traditionally we do it this way. So we're decreasing the water saturation. So the water relative permeability starts off as 1 and then it decreases and decreases and decreases until at a low saturation, the water's just in the nooks and crannies and actually some of the clay, and there's essentially no measurable flow of water, even though there's still water retained in the pore space. So that's what we see. The oil relative permeability starts at 0, but as we put more oil through the system, will increase. And it increases until it's almost 1. Not exactly 1, but it's very close to 1 because the oil has occupied all the larger pore spaces. The water's just in clays and regions where there's negligible flow. So you might say, well, then the oil takes virtually all the flow. And that's indeed what we see. Okay. Primary drainage. That represents what happens when oil first migrates into a reservoir, or when we first inject CO2 into the subsurface, for instance. The curve on the right is for secondary water flooding. What do I mean by that? That's where now I have oil and water present in the pore space, just like an oil reservoir on discovery, and now I'm going to inject water to displace oil. So here we start at a low water saturation and essentially a 0 relative permeability, and we put in more and more water. So the water relative permeability increases, the oil relative permeability decreases. Now let's just look at the shape here, because there are a few interesting phenomena. The first thing is this water relative permeability looks the same shape as here, but it ends. Right? It doesn't get much beyond about 10%. Why is that? It's because it's a water-wet porous medium. The oil likes being in the big pores away from the surface. The water likes being next to the surface. The oil actually tends to get trapped in the big pores, surrounded by water. So there's a residual saturation. There's a saturation about 35% of oil that's trapped in the big pores. And at that point, the oil can't be displaced anymore, so the displacement stops. Okay? And at that moment, the water relative permeability is still quite low because the oil is blocking its flow through all the big pores. The oil relative permeability, on the other hand, the oil relative permeability falls sort of almost linearly here because, of course, what happens is the water fills some of the smaller pore spaces. Maybe that doesn't make much of an effect, but of course it blocks some of the flow paths. You can imagine a road network where you start closing some of the roads. Even if you haven't closed the main road straight away, it's going to begin to block the traffic. So you see exactly the same. Lastly, what's also shown in the solid lines are predictions. These are predictions from what's called a network model. I'm not going to describe that, but this model essentially takes a representation of pore space and a description of displacement using ideas to do with contact angle and the Young-Laplace equation. Putting those together, you can actually predict quite nicely what happens. And so we feel that we understand this behaviour quite well. Now here are some other results. This shows the effects of wettability. Again, I'm showing the equation here, the multiphase Darcy law. I haven't put in the gravity term. The experiments normally, either where gravity is a negligible effect or in fact the flow is horizontal. So here we have a very similar graph. This is the water saturation here, is normally shown on the x-axis, the relative permeability on the y-axis, and should be obvious that there are going to be two curves here, and the one that increases with water saturation is water, and the one that decreases is oil. Okay. So what's shown in blue is a water-wet system. This is on Bentheimer sandstone, and the behaviour we see here is very similar qualitatively. We saw in Berea. Again, no surprise. The also shown is a mixed wet sample. So this is one where actually the oil has been inside the rock for some time, and surface active components of the oil have adhered to the solid surface. And so it's rendered the system more oil wet. In fact, it's mixed wet. Some bits are still water wet, still like water. Some bits are a bit oil wet. And so what do we see here in the mixed wet sample is a different relative permeability, even if we're looking at the same rock. We see that the oil relative permeability here drops very rapidly. Why? Because oil is no longer non-wetting phase. In fact, the water wants to move into some of the larger pore spaces. The oil is now confined to the narrower regions of the pore space, but of course there's less flow. So the oil relative permeability drops very rapidly. Okay? But you notice there's less trapping. You get this region here where the oil relative permeability is very low because the oil's in the nooks and crannies of the pore space, but it's much more difficult to disconnect it because it tends to be sort of clinging to the surface. So it's not trapped in a blob in the center of the pore space, it's clinging to the surface. And so you get a lower residual saturation. See, the water saturation goes up to 89%, so 11% is trapped, as opposed to, in this example, almost 40% of the water. The water relative permeability, you notice, also stays relatively low. I'm going to describe that in a subsequent video. But actually the water, although it goes through some of the larger pore spaces, only really gets well connected at a high saturation. But eventually the water relative permeability does go up because the water is actually occupying some of the larger pore spaces, and indeed almost 90% of the total pore space. So it gets a bit better connected. Okay? But its relative permeability does go all the way up to 1 or even close to 1. Here it's about 40%. Okay, so these are typical experiments that we can see. Here, the saturation has been obtained by imaging, and we can also either check or account for any variations in capillary pressure. So I'm going to end this presentation with just a sort of historical interlude. So the development of multi-phase flow in porous media was pursued more or less independently by both petroleum engineers, who were looking at subsurface flow in oil reservoirs, and hydrologists. In petroleum engineering, the idea was always to look at the flow of both oil and water, or oil, water and gas together. And it's Muscat and Meres who, in 1936, first presented the multiphase Darcy law in more or less the way I've presented it today. And at the same time, in fact, in the same issue of the journal, Wyckoff and Botzet presented the first measurements of relative. Maurice Muscat then published a book, The Physical Principles of Oil Production, which really sort of laid out much of the physics of flow in porous media. To my mind, established the discipline of reservoir engineering. The concept of capillary pressure was introduced by Miles Leverett in 1941. He made a number of seminal contributions to multiphase flow in porous media, which capillary pressure is just one. But in hydrology, the development, as I said, was largely independent. Here, there was less interest in the flow of two phases, really just the flow of water. But of course, the flow of water would be influenced by the water saturation. So it would be less if the saturation were lower. And Buckingham was the first to talk about multiphase flow, the concept of capillary pressure. Richards, in 1931, so this is before it was in the oil industry, then introduced the idea of the flow equation and introduced what's called the Richards equation, the flow of water in a multi-phase flow situation, so when there was air present. The interesting thing, though, is though we called about these two communities working independently, the slightly amusing thing is that Richards' original paper in 1931 is in the first volume of the Journal of Applied Physics. Muscat and Meres's paper is in exactly the same journal 5 years later, but does not reference any of Richard's work. So I'd have to say that maybe here it's the petroleum engineers who maybe should have been looking at the literature a little bit more carefully. Okay, so I will end it there. That was a brief introduction to what is a very subtle and complex topic on relative permeability. But at least at this stage, we know the equation. It is largely an empirical engineering approximation. There are lots of subtleties, but it works pretty well. It is something that can be measured and something that, at least in simple systems, is relatively well understood. Okay, I think we'll end there. Thank you very much.